Thank you very much, and sorry for the delay. My name is Massood Tabib-Azar, and this work was done by Mingming and Faisal, and also Pradeep Pai, who is in the audience. Right now I'm at NSF, so I am obliged to say that this is the work that was done, that is done at University of Utah, and it is supported by DARPA Microtechnology Office. So microplasma field effect transistors, there are lots of devices based on plasma, and these are kind of gaseous plasmas. You have basically two electrodes, and you apply a voltage, and you ionize the gases that induce two electrodes. And of course, light comes out when you ionize the gas. We have added a third electrode to control the amount of plasma that we generate between those two electrodes. So since they are based on ionization of gases, they are naturally kind of adept to environments where you have large ionization energies coming from nuclear reactors or whatnot. So one potential application of these devices would be in troubled reactors where you need some electronics that can operate under very harsh, intense radiation coming out of a reactor that is not functioning properly or is out of control. They're basically for very harsh environment type of environment. So I put this plate in order to show you that indeed you can simulate these things using COMSOL and finite element and show that there is a gate field effect that's shown. The gate is right there. Let's call this drain and source. In these particular devices, the voltage applied between drain and source ionizes the gas that's inside this chamber, and the gate, depending on how much voltage you are applying, whether it is positive, 0, or negative, you can push away different species that you have inside the plasma. So plasma is composed of positive ions and electrons. So if you put positive voltage on the gate, you're going to attract the electrons to the gate region and oppose or repel the ions that are usually positively charged. And if you put negative voltage, you do the opposite. So they're actually possible to have two different types of devices based on these plasma FETs. One based on attracting the electrons to the gate region, and the other one attracting the ions to the gate region. So depending on where you put your drain and source electrodes, you can have on and off devices that are complementary to each other. Now, when you have these electrodes and the gas inside in the same chamber, and you apply voltages to ionize the gases, what happens is that the electrodes get sputtered by the gases that you're ionizing. So what we have done is we have separated the plasma generation from the control that you have in the FET, and we call that separate plasma FET structure. And I'll show you the way they look. So this is kind of a schematic of where you have a separate torch that creates the plasma, helium or argon or whatever gas you want to create the plasma with, comes through this nozzle, and you have a structure that is very similar to FET that we are familiar with in CMOS. Now, what we are doing for this grant for MTO at DARPA is to come up with circuitry, not only one device or a couple of devices that work together, but also a circuitry that can perform certain useful functions. So this kind of shows the overall architecture. So we have this plasma generation plate there, and these are interdigitated transducers. So by applying a voltage between them, we create the plasma, which is more or less uniform over the circuit that is shown at the bottom. And since plasma is conducting, we need a shield plate in there to separate devices from each other in the plasma environment. This shows the picture of one of our devices. The circuit, the plasma FET structures are shown in there, and that's our distributed plasma source. Now, if you look at the plasma generation process, it's highly nonlinear. So as a function of frequency, you see these hysteresis, and as a function of voltage. So it's basically, you have to go to a slightly higher frequency in order to generate the plasma. Coming back, it shows this hysteresis, and also as a function of RF voltage, you get the same thing. And this is the actual picture of the device working under the plasma. So the kind of IDS versus VDS as a function of gate voltage that you get, our typical ones are shown in here. Our objective to make these as sharp as possible in transition, and also separate them as much as possible. So you can define transconductance similar to what you have in FETs for these devices, And these are actual devices under operation shown in there. The equations for IDS versus VDS for
and motivation.
voltage, you can derive them. It is very similar to what you get in semiconductors. So essentially what these are is that in semiconductors your dopants are fixed in crystal, and then they produce the electrons or holes. Here you only have electrons. In here, the ions that produce the electrons can themselves move around. So it is kind of a fluidic semiconductor medium. And the equations for plasma, by the way, they have known for a long time. So what we are doing is we are taking the same type of equations, Langmuir probe equations, and reducing in size for devices that we are fabricating. I won't go through the fabrication process, but it is very similar to what you typically see in a CMOS. These are some SCM pictures of three-dimensional structures that we have created. So you can see the drain and source, and these are underneath a gate that kind of goes over them and hugs them. So the idea is that the ions that are produced by the plasma torch that is sitting above this will come and then diffuse into the cavity region, and then the motion of the electrons or ions are controlled by the gate that hugs them. And we have different geometries in order to see the effect of a pointed structures for drain and source, or flat ones, and different gate lengths. So this is a little bit larger view of what we have. I would like to kind of focus on the cavity there. These cavities are produced by xenon difluoride etching of polysilicon that is used as sacrificial layer, and the metal gate underneath it has a ALD passivation layer so that the electrons cannot directly go through it, so it's kind of reduce the conduction for the electrons through the gate. We want the gate to be isolated as much as possible. The same concept that you have in MOSFETs based on semiconductors. So you can put these in parallel in order to increase the amount of current that you want to conduct between drain and source. So I'll go through experimental setup. That I showed you, it is really good for circuits, but in order to optimize individual devices, we have these torches that individually we can use to excite particular or produce plasmas for particular devices, as shown in there. And you get a variety of different type of IDS versus VDS. So depending on where the torch is with respect to the gate plate that I showed you, you can get different results. And based on whether you have a three-dimensional or two-dimensional device, that also affects the IDS versus VDS. So as I mentioned, our goal is to make this transition to be as sharp as possible and separate these curves as much as possible from each other. I will just go through some of the experimental results that we have obtained so far and emphasize some interesting features that, assuming that most people are familiar with semiconductors, kind of draw a contrast. You can using the plasma. So basically we have 4 contacts, and the plasma is generated between the 4 contacts in there. Some of these are kind of manually assembled. Some of them are based on microfabricated, as shown there. That the voltage between these 2 electrodes of the magnetic field that is applied perpendicular to the plane of this device. The voltage that you get between 2 electrodes as a function of magnetic field is kind of shown in there. So there is a saturation regime and there is a linear regime in the middle. The effective mobilities that you get, this is a combination of electrons and ions, can vary between 0.1 to 10 centimeters square per volt second. So compared to silicon, these are typically 10 to 100 times lower. So one has to do other things in order to speed them up for useful functions that you need to perform. This is another example of IDS versus VDS. I put that in there. Usually for planar structures where the gate doesn't go in the 3rd dimension, the IDS versus VDSs are much shallower, but they are nonetheless useful, and we have made some push-pull type of amplifiers using these. Now, if you put these devices inside a reactor, that's how I started my talk, that one of the motivations for these devices is to put them inside harsh environments with large densities of ionizing radiation. Their properties don't change that much. And actually, they like it better inside ionized environment than outside, because the radiation coming from the reactor helps ionize the gases. So the amount of voltage you have to apply for their ionization can be relaxed a little bit. So they're really good for operating in inside in deep space applications as well as reactors. Now, I kind of put this in the beginning, and also I would like to go back to it at the end. So this particular one, these two are for two different voltages of positive and negative. This is positive and this is negative. So when you apply the voltage, depending on whether the gate voltage is negative or positive, you can attract large amount of electrons near the gate, or you can, this is for electron density and this is for the ion density. So I have to kind of read it. For Vg is equal to 0. These are for Vg is negative and this is positive. So if you compare, for example, this guy to that guy, so we are looking at the ion densities. You can see that for this particular case, we have repelled the ions from the surface. This is the scale. We have repelled the ions from the surface of the region, and here we have kind of attracted them. So this is kind of effectively programming the doping in semiconductors. That's the parallel that you can look at. So by attracting the ions towards the gate or repelling them, since these ions have to be neutralized by the electrons, by the accompanying electrons, you can program the conduction of the breath. Ion control, which is shown in there, as well as electron control that are shown in there. This is for the electron concentration. Both of these operations are possible. Now, in order to speed these things up, electron mobilities are much, much higher than the ion mobilities, at least by 2,000 times. So by going into this regime of operation, you can make them much faster than by trying to control their conduction through the ionic concentration. So this is something we have learned during the past 6 months. To speed these things up, we really need to take advantage of these different type of controls that you can have inside the device. So in conclusion, we have actually continued. This is the second time we are presenting this. The first version of this was last year in Limerick. We have continued improving the three-dimensional microplasma devices. And now we have lots of quantitative data, and we have started modeling and understanding how to improve their performance. And we have